In this problem, we had a quarterback running forward, and this is the quarterback's vector. Okay, so that's what I'm going to do now. This is the quarterback's vector, and then the red is the vector that represents him throwing the ball. So that's B. So now I need to write these in component form. When a vector, so write this down, when a vector is purely horizontal or vertical, one component will be 0. Okay? So if this is horizontal, then it only has value in the x direction, because that's the horizontal direction, and 0 in the y direction. Okay? Okay, and then if it's not vertical or horizontal, okay, if not vertical or horizontal, then that's an if-then statement. Then it's B cosine theta, B sine theta. B cosine theta, B sine theta.
What does B represent?
B is the magnitude of the vector, so like it's or it's V. So in this, so it's the magnitude. So it's the magnitude of this. So if this has a magnitude of 25, then 25 cosine theta, 25 sine theta. All right? Okay. Now we did that. Okay, so now the green one is blue plus red. So now I have blue and I have red. To add, I add like matrices. The first components add together. The second components add together. This is where calculators come in. And you're going to write this as 5 plus 25 cosine 40. You literally put it in your calculator in degree mode. And you get 24.15, 16.07. I will specify the place value. Okay? Okay, that's all fine and stuff, but I need resultant speed and direction. So, right. So, when it says resultant speed, that is magnitude. So, the magnitude is that. And it's going to be the square root of the green vector elements squared and added. So 24.15 squared, 16.07 squared. Yes? Yay. Okay. Then that's the magnitude. And then we put that in our calculator and we get 29.01 meters per second. So he's running at 5 meters per second. He throws the ball at 25 meters per second. The ball then is flying at 29.01 meters per second. Had he been standing still and he threw it at 25, discounting friction and all of that, it would have continued at 25. Had he been running at 5 and like he launched something, horizontally, then they would have at 25, then they would have added 5 and 25, 30. But because his direction and the direction of the ball are not parallel, they add like a vector. And so it's the 5 and then the 25 together, it'll be 29. Okay, that's a little bit on the physics side, but it gets you to understand the numbers. Okay? So now the magnitude is 29.01. The direction, okay, for the direction, you're always going to do inverse tangent y over x. Always. Always. At 1 a.m., at 5 p.m. in France, in the southern hemisphere, everywhere. Yes.
It's like when I'm doing like the homework problems for some of them, they'll like describe like the direction, like subtract it by like 360 and get like the other side.
I'll talk about that right now.
And that's just confusing.
Yeah. I'll talk about that. So that's going to be, yes. So I go here, and it's this over this. So 16.07 over 24.15, that's 33.6. Okay. Let's think about that for a minute. 33.6 degrees, yes. Let's think if that makes sense. This, we said, had an angle of 40. You see the green line? It's tilted a little bit lower. That has a direction of 33.6. Okay, so if we drew it perfectly to scale, it would have been, more obvious. So,
Is the opposite, is the angle on the adjacent angle to the 40-degree one? Is that one the 140 because it's
this one here?
Yeah, that's the whole angle, right?
Yeah, but we don't care about that. Okay. All right, so okay, so take a look at 51. This is important. So 51, how does it look? It's
Do you want us to draw it out?
No, you don't have to draw. So you don't have to draw it out for me, but you should know in your mind what these vectors look like. So 3 and 1, 2, 3, 4, 5, 6, 7, 8 looks like this, right? Okay. Now, the angle for these vectors is always measured from this horizontal line counterclockwise. So it's always measured that way. So that's the angle that you want. So now, if I want the angle here, it's inverse tangent of -8 over 3, right? And if I put that on my calculator, inverse tangent of, what is it? -8 over 3. It's -69 degrees. Is that right? Okay. So theta is -69.4 degrees. Let's say I asked for 10th place. Okay, that's that direction, which is not what I want. So how do I get the positive direction? That's 360 minus 69.4, right? Because I don't want you to plug into a formula. If the angle is -69.4, that means that angle is 69 degrees. Absolute value of it is 69 degrees. And if I want this, then it's 360 minus that. So always, always, always draw your angle, and then, make sure that your value represents that. This one, 8.3, is now moving on 1 or 2 steps more, right?
This is not on the quiz,
No,
right?
correct. This is not on the quiz. So we're talking about dot products, and we're talking about vector projections. At the end of the day, in the real world, it's all about dot products, okay? So what is a dot product? Suppose you have 2 vectors, A and B, and they are connected like, what it says here. This is how they're related. Okay, now, if you shine a light, suppose you shine a light onto A like this, right? So like you have a flashlight like this, right? And then you shine a light like that, okay? Vector A will create a shadow onto vector B, right? Okay, now, this shadow is called the projection of A onto B. So I'm literally holding a flashlight like this here. It's perpendicular to this, but you don't have to worry about that. And then there's a shadow cast here. That length of shadow is called the projection of A onto B, and this is how we write it. Okay? Projection of A onto B. Okay, now, if we were to take the length of this projection, okay, so that's a length, right? If we were to take the length of that projection, that's a number, okay, 5 centimeters, 12 centimeters, and multiply it by the length of this vector, okay, that's the dot product. So let me say that again. Does everybody understand that there is a shadow here? That shadow is called projection. If I were to measure that shadow, 7 centimeters, measure the entire green vector, 12 centimeters, multiply them together, that's the dot product. Okay? So how did I get that? I multiplied two whats? Two lengths, two distances, two numbers. And what did I get? Did I get a number or a vector? If you multiply two numbers, what do you get? A simple number. So that's the dot product, right? And the way we write it is A dot B. That means dot product. Okay? And that would equal a number, a scalar.
Even though A is enough, like the value A is being used.
Okay, so the way we do it, the way it's done, A dot B, how do you multiply vector? Okay, how do you do A dot B? If vector A has components A1, A2, and vector B has components B1, B2, then the way you do it is A1 times B1 plus A2 times B2. Okay? So A1 times B1 plus A2 times B2. Okay. All right. This, I left space here for us to actually like go through the proof, but because of time, I think this year I'm going to skip it. I might go back to it later, but I'm going to skip it for now. But now, let's think about this for a minute. Let's think about this. Suppose this is vector B, and suppose this is vector A. Okay? And they're perpendicular. If I were to shine a light here, how much shadow would A cast onto B? 0. Does that make sense? So, if dot product equals shadow times B, if the shadow is 0, how much is the dot product? 0. So if the two vectors are perpendicular, the dot product is 0, and that's the reason why. Now, perpendicular is cool when we're talking about lines, but most of the time when we're talking about vectors, we call it orthogonal, right? So here's a question for you. What does the orthodontist do to your teeth? Makes them straight, right? And what does an orthopedic doctor or surgeon do? Makes your back straight. So ortho, right, has that, you know, of like straight or proper or whatever, right? So orthogonal means, and gon, right, like polygon, it's number of, like it's line. So orthogonal, you get why it's perpendicular, okay? So if the angle between two vectors is 90 degrees, then none of vector A can cast a shadow, and the dot product will be 0, And so we say the two vectors are orthogonal. And the way we write it is A dot B equals 0. Okay, so let's do A dot B here. This is very, very straightforward. So we're going to find the dot product of U and V. We do U dot V equals this times this, negative 3 times 3, plus 4 times 6. And you just get a number, in this case 15. That's it. It's not a scalar, it's not absolute value, it's nothing. It's just U dot V is 15. Here, U dot V, 2 times negative 14, negative 28, plus 7 times 4, 28, is 0. So these two are orthogonal. Okay. Okay. Dot product is commutative, and you can use the distributive property on the dot product. Scalar multiplication works just like we know. Okay. Here, if you do U dot U, it's just the magnitude of U squared. Okay. So let's think about that. What if we're going to do A dot A? So this is vector A, and then this is another vector A. And if we were going to do A dot A, and if you're shining a light, how much of A is being cast onto the bottom A? All of it, right? And so if I multiply the shadow times itself, what have I done? Magnitude squared, right? I just multiply A by A squared. Okay? So take a look at this. How do we use the dot product to find the magnitude of A? What's the magnitude of A, like we did yesterday? The square root of 6 squared plus 5 squared, root 61, right? What if you did A dot A because you're flying somewhere and you have lots of time and you're like, let me just create vectors and find their, projections onto itself, right? A dot A. So what is that? Negative 6, 5 dot negative 6, 5. Where are your notes? Henry, where are your notes? Where's your note packet? Okay. Take notes. Okay. Let's go. So what's A dot A here? 36 plus 25. What's A dot A? 61. Okay? What is that compared to the magnitude? It's the square of the magnitude. So A dot A is really the square of the magnitude. Okay? Oh, yeah. All right. Okay. So let's talk more about A dot B. Just a sec.